Dear students, welcome to lecture number 32 of the Signals and Systems course. In the previous lecture, we saw DTFT of some of the commonly used signals. So we saw DTFT of some of the signals. We derived the DTFT of a constant discrete time signal where x of n is equal to 1. We saw how the response, how the frequency domain representation for constant dt constant discrete time system contains impulses. It is still periodic. I also showed you some of the computation plots for visualizing the phase and magnitude of x of omega, and then we also saw some more examples. Towards the end of the lecture, I had given you an assignment to derive the DTFT of u of n. So that is what we will be doing today. I hope many of you tried to derive it on your own. So basically what we want to derive is DTFT of u of n. So x of omega is summation x of n e to the power j minus j omega n, right, and n goes from minus infinity to plus infinity. Here we should note that x of n would be 1 for n greater than equal to 0. So we had solved a similar problem in the previous lecture where we had derived the DTFT of a to power n un. Here a was greater than 1. So this was a converging signal. So as n increases, the magnitude of x of n was diminishing. So that's why we were able to apply directly the geometric progression formula for infinite series, and then we got this. So here if we can't directly apply the limit a tending to 1 in this signal, because in this summation, because we direct cannot apply, because we will get a non-converging series. So what do? We have solved a similar problem for continuous time signal. What we do is we would define another signal . This is 1, this is 2. So we would define another signal, say a, which diminishes with increasing n. So we would define x of n as, say, limit a going to 1, a to the power n un. So we can apply the limit to the previous problem and then we can derive it, but using that method it becomes a bit more complicated. So I would be using a different approach. There can be multiple approaches in deriving the Fourier transform of u of n. So the approach which I will be using is, I will be breaking this signal into an odd and even component, and then I want to use the previous. I again don't want to apply the limits and get the impulse functions in frequency domain. I have already done it for a known signal. So I have already done it for the case of this signal. So when I was deriving this, I have already derived it. I have already applied the limit a going to 1, and we got the impulse function. So what I want to do is, I want to use this this result to directly get the answer for the DTFT of u of n. So what I would do is, So you must notice that u of n is neither even and neither even nor odd function of n. So from the previous properties which we had seen, it should be very clear to you that x of omega would neither be purely real nor purely imaginary. It would be a complex signal. X of omega would be complex. So I can break x of n into, so I can break x of n into x even of n and x odd of n. So this would be my even function and this would be my odd function, and x even of n is related to x of n simply as x of n x of minus n divided by 2, and x odd of n as x of n minus x of minus n divided by 2. So in this case, in this particular example, I can write x even of n as limit a tending to 1 a to power n un plus a to the power minus n un divided by 2, and similarly I can write x odd of n as limit a tending to 1 a to the power n u of n minus a to the power minus n u to the power u of minus n. Yeah, there is a typo here. There should be u of minus n. Right. So now if I take the DTFT of the even component, I would get x even of omega as limit a going to 1 Fourier transform of a to the power n un plus a to the power minus n u of minus n by 2. Oh, so there's a minus 2 divided by 2 here as well, right? So if you look at this signal, this is simply so here when n is equal to 0, this is 1 and this is also 1, so you get a 1 here, and when n is equal to say 1, you get you get 1 by a by 2 here, and here you get a square by 2. Here also you would get a by 2, here you would get a square by 2, and so on, right? So I can write this signal as in the familiar form as x of omega is limit a going to 1 Fourier transform of a to the power mod n plus delta n into 1 by 2. Yeah, look into it how this signal and this signal comes out to be the same. I mean, if you want, you should pause the video and look into it. Right. So we already know what is the Fourier transform of this part, and we also know what is the Fourier transform of delta n. So we would just use that property. So XE of omega would be limit a going to 1. Fourier transform of this is, we had derived it in the previous lecture. Yeah, so Fourier transform of a to the power n comes out to be 1 minus a square divided by 1 minus 2a cos omega a square. So what we have is 1 minus a square divided by 1 minus 2a cos omega plus a square, right? And this is multiplied by half, and then DTFT of del n would be 1, so you would get a half in here. So let's keep this. We will use this. Yeah, so let's keep this. We will use this shortly. What about the odd part? So x odd of omega would be limit a going to 1 Fourier transform of u of a to the power n un minus a to the power minus n u of minus n, right? So basically limit a tending to 1 Fourier transform of a to the power n un minus Fourier transform of a to the power minus n u of minus n into half. So we already know what is the Fourier transform of a to the power un. This also we had solved in the last class. So Fourier transform of a to the power n un is 1 by 1 minus a e to the power j omega n. So we have x odd of omega as limit a going to 1 upon 1 minus a e to the power minus j omega minus, what is this? This is Fourier transform of, so we know that if x of n has a Fourier transform of x of omega, then x of minus n has the Fourier transform of x of minus omega. So we had derived this in lecture number 28-29. If you are not familiar with this, you should go back to those lectures and refer to them. Refer to the derivative, refer to the property. So this would be simply, if I want to write this, this would be simply 1 divided by 1 minus a e to the power plus j omega. Is that correct? Right, so check it on your own. You must check this on your own. Right? So now x of omega is x even of omega plus x odd of omega. So x of omega is limit a going to 1 minus a square, there is a 1 by 2 here, 1 minus a square 1 minus 2a cos omega plus a square plus 1 by 2 plus limit a going to 1 upon 1 minus a e to the power minus j omega minus 1 upon 1 minus a e to the power a e to the power j omega. Is that correct? Yeah. So now I'm just rearranging the terms. Limit a going to 1 by 2 1 minus a square upon 1 minus 2a cos omega plus a square, this half, oh there is a 1 by 2 here as well. Right, the 1 by 2 coming from this part, 1 by 2. Yeah, I missed 1 by 2 here. So 1 by 2 plus limit a going to 1 by 2 plus 1 upon 1 minus a e to the power minus j omega minus 1 upon 1 minus a e to the power plus j omega. So I will combine these two terms. This is 2. Combining these two terms, I get x of omega as plus a square a going to 1. So you should rearrange this. I am just skipping few steps so that we can cover it in a shorter time. Right, so let me directly write the simplified version. So there will be 1 by 2 here. This will be 1 minus a e to the power minus j omega. There will be a plus sign here, and this divided by 1 minus 1 by a e to the power minus j omega. E to the power minus j omega. So when you apply the limit on both of these, in the first term we have already seen that this comes as a summation of impulses, and this there is no so these two terms will become equal when you apply the limit a tending to 1 here. So you will simply, and these two will be equal, so this half will cancel out. So you will get x of omega as pi, because earlier there was a 2 pi, so the 2 pi 2 cancels out with this 1 by 2, and this you have summation over m delta of omega minus 2 pi m plus 1 upon 1 minus e to the power minus j omega. So you should derive this expression on your own with this method or by any other method. If you have an interesting method other than this, you should post it on in the discussions section on Moodle. This expression is given in example 5.8 of Oppenheim book. They have derived this expression using the accumulation property, and in the section number 5.3.5 differencing and accumulation property, they have not derived the accumulation property. They have used the accumulation they have given the accumulation property, which is similar to the discrete continuous time integration property. So at this point you should derive this unit step function, and then you should also derive the accumulation property. So that would be an assignment for you. I won't be doing it. Derive the let me type it out. Derive the accumulation property of DTFT. Right. So let us see another example. Another simple case. I think this was D, so let's take the example F. When x of n is equal to 1 for mod n, n1 and 0 when mod n is greater than n1. Right, so this is what, if you want to plot this signal, this is so this is simply so this is 0, and this would be n1, this would be minus n1, and your x of omega would be simply summation of n over minus n1 to n1 e to the power minus j omega n. Right. So do this as an assignment. I am simply writing the answer. So you will get GP and a finite GP, and then you can write the you can write use the formula to get the expression. What you should do is you should simplify the expression in this form: sine of divided by sine of omega by 2. So you should be able to show this. So as you might guess from this expression here, when n1 goes to infinity, you should get a constant constant signal of amplitude 1, and its Fourier transform should again give you a summation of impulses. So this expression in the limit n1 goes to infinity also should reduce to the unit impulses. No, I mean unit impulses multiplied by 2 pi. Right, so you should show this on your own. Let me give you another 2 examples and then we will stop this DTFT part. So f, how many is f? So if x of n is delta of n minus n naught plus delta of n plus n naught, here you have to simply, this is quite straightforward. You should be able to show this as this comes out to be cos omega n naught. Another example, let x of n be sine pi by 3 into n plus pi by 4. So this is again straightforward. You write x of n in terms of the complex exponential, so this would be e to the power j pi by 4 e to the power j pi by 3n minus e to the power minus j pi by 4 into e to the power minus j pi by 3 into n, right? And we have derived the DTFT of 1 is 2 pi summation, here there is divided by 2j as well. So if I miss out some such step, you should point that out in the discussion section on Moodle. And summation over n. So using frequency shift property, e to the power j into omega naught n as a Fourier transform of 2 pi delta of omega minus omega naught minus 2 pi m. So you should use this property on this signal, right? And then you should finally write what is x of omega, right? So again, I am not giving you the answer for this. Right. So let us now take couple of examples on computation of inverse discrete time Fourier transform. So So we can compute IDTFT, inverse discrete time Fourier transform, using the synthesis equation. That's straightforward. So basically x of n is 1 by 2 pi integral over 2 pi x of omega e to the power plus j omega n d omega. Here n is an integer, right? So if I give you an example that x of omega is shown in this figure. So let me draw you yeah. So and so on. So this is minus pi, and this is pi, and the magnitude here, note, is that 2j, not 2 but 2j, and here the magnitude is minus 2j. So this is your x of omega. Now you want to compute x of n. So it's simple, you just use this formula and solve the integral. So basically x of n is 1 by 2 pi integral minus pi to 0 minus 2j into e to the power j omega n d omega plus integral 0 to pi 2j e to the power j omega n d omega. So you solve this integral, and finally you would get the solution is minus 2 upon pi by n into 1 minus cos n pi, right? So n is an integer. I can also write this in this form of sign. So I can write this as 4 by pi n, 4 by pi n into sine square pi n by 2. Note that this is a odd function of n. You should have guessed this because here x of omega was imaginary valued. Signal, right? So x of omega was purely imaginary. So x of n should have been an odd signal as it came out. Right. So I will post a few more questions on Moodle. I will stop here because the file size would again increase. So in the next, I will post a tutorial for on DTFT. If there are any doubts, you should post it in the discussion session on Moodle. In the next class, I will introduce you to the discrete Fourier transform. How is it different from discrete time Fourier transform? What is the new interesting feature? What are the new interesting features which are introduced when we sample the signal in the frequency domain as well? So we discretize in the time as well as the frequency domain. So what do we get? So I will stop here. Next lecture will be uploaded soon. Good day.